Converting gives about 14 billion years, which is a very rough approximation for the age of the universe.
This has got to be a coincidence. Today we're looking at a heavily requested channel, Joseph Newton. Specifically, cursed units. There's a lot of weird units in nuclear engineering, so this should be really interesting. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer, a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This video looks at 4 of them, which gradually build in cursedness.
Cursedness.
Let's start with another unit in common usage, kilowatt hours. When we say something like,
so kilowatt hours shows up a lot. It's how you get billed for electricity at your house. So it's fairly ordinary. Maybe we're all just used to how cursed it is.
miles per gallon or meters per second, we have a simple intuition for that. How many miles can you drive on 1 gallon of fuel? How many meters is something moving each second? But just as you can divide units, you can also multiply, and this has a different sort of intuition. If your washing machine is running at a power consumption of 2 kilowatts, and it runs for 5 hours over the course of a week, the total amount of energy it uses in that week is the product of the two, 10 kilowatt hours.
To give you a sense of scale, in nuclear engineering, you mainly look at it in terms of megawatt hours. For example, a nuclear power plant typically produces about 1,000 megawatts of electricity. Granted, the reactor itself is usually well over 3 times that, but steam cycles are around 33% efficient. So we get paid for about 1,000 megawatts. So a nuclear power plant gets paid for about 1,000 megawatts. In this example, the one I worked at was a little bigger, sometimes between 1,300 and 1,400 megawatts, but let's just keep it simple. So 1,000 megawatts. So nuclear power plant every hour produces 1,000 megawatt hours. Other energy sources use megawatt hours as well, but you can see how little uranium it takes to make a megawatt hour compared to something like coal or natural gas.
Like miles per gallon though, we can do some unit cancellation. A watt is actually a joule per second.
Yep.
How many joules of energy is something using every second? So we've got energy divided by time multiplied by time, and since there's 1,000 watts in a kilowatt and 3,600 seconds in an hour, 1 kilowatt hour is actually equal to 3.6 megajoules.
Yep, pretty straightforward. By the way, a joule is such a tiny unit of energy. The cost per kilowatt hour where I live in Texas is on the order of 12 to 16 cents, so a joule is really a tiny, tiny amount of energy. Another way of looking at it is if you eat 2,000 calories per day, you're eating 8.3 million joules a day.
You can maybe see now why I think kilowatt hours are cursed. Let's say you wanted to estimate the distance from your house to the beach, and let's say it takes you 20 minutes to drive there, and accounting for traffic, your average speed is about 60 kilometers per hour. Since distance is speed times time, you convert the 20 minutes into a third of an hour and multiply by 60 kilometers per hour to get 20 kilometers. That's what a normal person would do. Writing kilowatt hours is like multiplying the 60 kilometers per hour by 20 minutes and then writing your answer as 1,200 kilometer per hour minutes.
That is awesome. See, I never really thought about it like that. Maybe I'm just so used to thinking in terms of energy like that, working in nuclear power. But I guess I can see. One thing I'm curious about is how many people, when they look at their electric bill, even pay that much attention to the kilowatt hour breakdown, or they just look at the big number that goes through the roof in the summertime, at least where I live, because we're running our AC so much. Maybe I'm just
We'll
used
see
to it.
more of this cancellation later in the video, but first I want to say something about this general process of multiplying and dividing units.
I'm not sure where he's going with this one.
Most physical constants have units. For example, the gravitational constant, which relates mass to gravitational force, has units of cubic meters per kilogram per second squared. Let's see where this unit comes from. The gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them. That means that the gravitational force between two objects is equal to the product of their masses divided by the distance between them squared, and then multiplied by some conversion constant, g, which we don't know yet but is the same for every pair of objects. To verify this, you can either do an extremely precise measurement with extremely precise equipment, or you can do a bunch of maths to this model to derive the orbits of the planets and then do some astronomy to see if it lines up with the actual orbits of the planets. If you do this, and you're working entirely in SI units, you'll get that g is about 6.67 times 10 to the minus 11. But there's a problem, the units in this equation don't match up. We've got force on the left, and mass squared over length squared on the right. So let's rearrange things to get this constant g by itself. Now we can see that g is actually in units of force times length squared divided by mass squared. If we then use the fact that force is mass times acceleration, and acceleration is velocity divided by time, and velocity is length divided by time, we get units of length cubed divided by mass divided by time squared. And this isn't just a technicality. If we're working with different units, the gravitational constant will need to be converted into those units.
I remember that when, at least I remember in my physics classes, because there'd be a unit, like the electric constant is the same way, or the permittivity of free space, which is a way of measuring the resistance when you form an electric field in a vacuum. It's about 8.85 times 10 to the minus 12 farads per meter, or coulombs squared, a unit of charge, divided by Newton, a unit of force, times meter squared. Yeah, I definitely get why constants are cursed. They're just a number you need to stick in your reference table.
For example, if we were measuring mass in pounds and length in feet, we wouldn't get 6.67 times 10 to the minus 11. Instead, we would get 1.07 times 10 to the minus 9.
That's painful, converting those units.
This process of only looking at the units in an equation is called dimensional analysis, and amazingly, it can actually be used to figure out what equation you should be using in the first place. There's a good number file video on this that I've linked in the description. Okay, those examples were both pretty quick. The next one is going to take a bit longer to explain. It's called the Hubble Constant, and it's measured in kilometers per second per megaparsec. Oh boy. Let's start with some history. During the 1920s, physicist Alexander Friedmann derived a model for the shape of the universe based on Einstein's field equations, suggesting that the universe could be expanding, a result supported by the fact that distant galaxies always seem to be moving away from us. Several years later, multiple researchers, including Georges Lemaitre and Edwin Hubble, independently found estimates for the rate of expansion. The idea is as follows. Take a sample of a whole bunch of distant galaxies, and for each galaxy measure two things: how far away it is, and how fast it is moving away. If the universe is expanding, then we would expect galaxies further away to be moving away faster. So take all the galaxies and plot them on a graph, with velocity on the y-axis and distance on the x-axis. The galaxies tend to fall along a straight line, and the slope of this line, now called the Hubble Constant, describes the rate of expansion of the universe. If you do all the measurements, you get a slope of approximately 70. 70 what? 70 kilometers per second per megaparsec. That means if a galaxy is 1 megaparsec away, it's moving at roughly 70 kilometers per second away from us.
To give you a sense of scale, a megaparsec is a little over 3.2 million light years. Not a number that comes up that often in nuclear engineering. Not yet, anyway. Not building any hyperdrives or anything like that.
If a galaxy is 10 megaparsecs away, it's moving at roughly 700 kilometers per second away from us, etc. Okay, but why megaparsecs? What is a parsec? It's about 3 times 10 to the 16 meters, and to explain why we're using parsecs, I need to explain how you actually measure the distance to a faraway galaxy. If you look at something in the sky and it looks small, it's hard to tell if it looks small because it's actually just small, or if it looks small because it's far away. The way you get around this is by pointing 2 different telescopes in 2 different locations at the same object, and measuring the difference in angle between them. You can then do some trigonometry to figure out the distance. The way we define a parsec is as follows. The distant object is 1 parsec away if the angle between the 2 telescopes is 1 arcsecond, and the distance between the telescopes is 1 astronomical unit.
I never actually knew how it was really defined. I mainly heard of parsec through sci-fi, like in Star Wars, Han Solo making the Kessel Run in less than 12 parsecs, which I'm guessing navigating something over a relatively short distance is a testament to his piloting and navigation skills. Sure.
What is an arcsecond? It's a 60th of a 60th of a degree. And what's an astronomical unit?
Yep.
It's the distance between the Earth and the Sun.
That chord. I mean, sure, I knew about astronomical units.
How did we get two telescopes that far apart? Well, it's easy. You actually only need one telescope. Just take one observation in January and a second observation in July.
True. Yep.
So you have two observations with a distance between them of 2 astronomical units. I don't know where the 2 factors in. Obviously, I'm brushing over a lot of details here.
Sure. I mean, it's an approximation because it's from Earth to the Sun and then another Earth to the Sun, but it's not a perfectly circular orbit, so sure.
So if you're an astronomer and you're doing lots of measurements on a daily basis, it makes sense to record distances using parsecs, because it follows directly from how you measure things in practice. The speed of galaxies, on the other hand, is calculated using redshift, the Doppler effect for light, and for this, there's not really any reason to use anything other than SI units. So when we're comparing velocity and distance, we get a figure in kilometers per second per megaparsec.
So Doppler shift comes up quite a bit in nuclear engineering. So the basic Doppler effect is the change in frequency or wavelength of waves due to relative motion between the source of the waves and the observer. You hear this when, say, an ambulance drives past you, how the pitch changes when it's coming towards you versus when it's going away from you. And when controlling a nuclear reactor, one method, which is built into how nuclear fuel works, is resonance absorption of neutrons. That is to say, the neutrons just get absorbed. They don't cause fissions. And this happens in the fuel, the uranium-238. Not the 235 part that causes the fissions, but the 238 part. It just absorbs a neutron instead of causing a fission. So in the reactor, blue shifting in a reactor is absorption frequency goes up because the relative velocity is such that the fuel atom appears to be moving towards an incoming neutron. So that relative velocity goes up, causing the neutron's energy to appear higher relative to the moving fuel, increasing the likelihood that it's going to get absorbed. Redshift is the opposite. Fuel atom appears to be moving away from the inbound neutron, which lowers its probability of being absorbed at the higher energy level. And the net effect of both of these things, because as temperature goes up, that's temperature of the fuel going up, the atoms are moving more and more vigorously in all directions, and the resonance absorption peaks broaden. This is also called Doppler broadening, and that means neutrons of a wider range of energy are absorbed. Again, during a redshift, it's more likely to be absorbed at low energy, and during a blue shift, it's more likely to be absorbed during high energy. But you have more red and blue, so you have more neutrons being absorbed. The end result is, when you raise the temperature of the fuel, the odds of absorption go up, and reactor power goes down because you're making less fuel. And which is nice because raising reactor power raises temperature, so it's one of the ways that power levels level off naturally. And this is all independent of control rods and reactor system control. This is just something that happens naturally. So it actually makes reactor control easier having this sort of effect. It's really convenient for people designing reactors.
But once again, we can do the gallons per mile trick. We're dividing velocity by length, and velocity is length divided by time, so if we convert the two lengths into the same unit, we get that the Hubble constant is about 2.3 times 10 to the minus 18 inverse seconds.
Inverse seconds.
You can check this by yourself. Type into Google 70 kilometers per second per megaparsec in this format, and it will convert it for you into 2.3 times 10 to the minus 18 hertz.
Yep, hertz, it's frequency. Frequency in hertz is inverse seconds. So when you look at how many gigahertz your computer has, or the speed at which your computer processes instructions, you're looking at billions of inverse seconds, which is pretty funny.
Okay, I have something else to explain. Hertz is a measure of frequency, and it's equal to inverse seconds. Why? Well, let me give an example. Let's say a sound wave has a frequency of 100 Hz. That means 100 waves are entering your ear every second. A different way to measure this would be to measure the time interval between two consecutive waves,
True.
which in this example would be 1/100th of a second. So you can see that the period of a periodic process, measured in seconds, is the reciprocal of the frequency, measured in Hertz. So to make sense of the Hubble constant, let's flip it upside down to get a number in seconds. Converting gives about 14 billion years, which is a very rough approximation for the age of the universe.
What? How did... This has got to be a coincidence. There's... Varying the frequency of the universe isn't going to affect the age, is it?
Now, the intuition behind this is as follows. Suppose a galaxy is moving away from us. If we assume it's always been moving at the same speed, then at some point in the past, it must have been right next to us. How long ago was this? Well, time is distance divided by speed, so it will be the distance to the galaxy divided by its velocity. But this is just the reciprocal of the Hubble constant, so the galaxy began its journey away from us 14 billion years ago. But this is true for every galaxy. That means 14 billion years ago, all the galaxies in the universe were on top of each other.
Sure, all the matter in the universe was just a lot smaller in terms of volume, but everything was all packed in. This was from the Big Bang before the inflation period.
And that sounds an awful lot like the Big Bang. Now, as it turns out, this explanation is actually completely wrong.
Okay, you had me. I was just trying to think of the implications of that. That was good. They had me going for a second.
The rate of expansion of the universe has changed dramatically over time, so there's no reason to expect galaxies have always been moving at the same speed. The Hubble constant is not actually constant in time, but rather constant across all galaxies at each fixed point in time. This is why it's sometimes called the Hubble parameter instead.
Sure.
What makes this so particularly cursed, though, is that the actual age of the universe is about 13.7 billion years, which, in an absurd coincidence...
This is awesome. You could use this to just mess with people.
is extremely close to the 14 billion figure provided by the Hubble constant. Why are these two numbers similar? There is no reason for these two numbers to be similar. Is there an intuition for the Hubble constant measured in Hertz? Sure, it's how many times the universe can expand from the Big Bang up to the size it is today in the span of a second. Right. I guess some ways of writing units just don't have a nice interpretation.
That was a good one. I like that one.
Now, as we saw in the gravity example, units sometimes just pop out of equations without any explanation. In this context, it's often more natural to write negative exponents for division, so instead of writing cubic meters per kilogram per second squared, we write meters cubed.
That's actually easier to read to me, because it looks like, you're having two division signs, so the second one looks like it should be in the numerator. So I prefer the inverse exponents, actually.
Times kilograms to the -1 times seconds to the -2. But this raises a question. If we can get negative powers, then can we get fractional powers? Can we get irrational powers?
Oh yeah. That gets weird, but sure.
As it turns out, yes. Occasionally you need to describe a relationship which follows a complicated power law, and that power carries over to the exponent on the units. There's one particular example that I want to go through, one which I encountered while writing an assignment for an optics course. It's called polarization mode dispersion, and it has units of picoseconds per square root kilometer.
Yeah, or maybe you could just put your kilometer to the -1/2. I don't know this one at all.
The speed of light in a vacuum is constant, but inside a substance like glass, light slows down, and the amount by which it slows down depends on properties of the light like frequency and polarization. This is why a prism can be used to split light into its component colors.
This property is also how, in certain contexts, you can go faster than light, such as the blue glow you see in a nuclear reactor. Now, this reactor is shut down for refueling. You can see they're moving the fuel with their submarine crane during a periodic refueling cycle. But the blue glow, the Cherenkov radiation, is a result of particles traveling faster than light. Now that's faster than light in water. So you could argue that you're being cursed just by virtue of breaking the light barrier. But the only restriction is you can't go faster than c, which is about 3 times 10 to the 8th power meters per second. But water slows it down to about 2.25 times 10 to the 8th meters per second. And a particle, for instance, an electron, which is produced from beta decay of fission products, is accelerated to a speed that exceeds the speed of light. Let's say it's going at 2.4 times 10 to the 8th meters per second. It produces Cherenkov radiation, and that's because it disrupts the local electromagnetic field, causing the emission of electromagnetic waves, or light. It's kind of like the sonic boom that occurs when you break the sound barrier. You're just breaking the light barrier. That's what the fun blue glowy thingy is in a nuclear reactor. It's breaking the light barrier.
Each color is a different frequency and moves at a different speed through the prism, resulting in it bending in a different direction. This is a big problem for optical fibers, which use light to carry information. A single pulse of light can be split up into component frequencies which all move at different speeds through the fiber. The overall effect of this is that the pulse gradually changes shape and spreads out as it travels, an effect called dispersion. Dispersion limits the rate of information transfer because you need to send pulses far enough apart that they don't blur together. Dispersion is measured in units of time, typically picoseconds. If you send a perfectly narrow pulse through the fiber, the dispersion is essentially the delay between the front of the pulse and the back of the pulse reaching the end of the fiber.
Picosecond is such a small unit, 10 to the minus 12 seconds, but here you're just talking about individual light events. So I guess it makes sense for an even smaller unit, and that's fast, even in the context of nuclear reactions. A weird unit for nuclear is the shake, which is 10 to the minus 8 seconds. And that is about the speed of fission events occurring in a nuclear bomb. So here we're dealing with something that's on the order of 10,000 times faster than that. All right. So in a nuclear bomb, by the time you're observing it with your eyes, at a safe distance, of course, the nuclear reaction was already ancient history by the time the beam of light hit your eye and your brain had the time to interpret what just happened. This is 10,000 times faster than that if you're measuring it in picoseconds.
There are a couple of different kinds of dispersion. The one I've just described is chromatic dispersion, where the different frequencies move at different speeds. This builds up linearly over the length of a fiber, so it's measured in picoseconds per kilometer. How much does the pulse broaden in picoseconds for every kilometer traveled?
Yeah, that's not too
Depending
bad.
on the fiber, there are ways to counteract this, but once you've accounted for it, you run into a different kind of dispersion called polarization mode dispersion, or PMD. Light is made up of oscillating electric and magnetic fields, and the angle of these oscillations is called the polarization. PMD occurs when different polarizations move at different speeds through the fiber. This seems strange. If the fiber is perfectly cylindrical, then surely it doesn't matter whether the light is oscillating vertically or horizontally. But that's the point, it's hard to make something perfectly cylindrical.
Yeah, making something perfectly cylindrical is pretty hard to do. Just like in the context of designing a nuclear reactor, if you want to have a perfect fuel distribution, make the reactor a sphere and make all of your layers of nuclear fuel and your control systems, such as control rods, perfectly spherical. And any system you inject for reactivity control, such as boric acid, which is basically liquid control rods, to basically spit out in perfect spherical outward expansions within this magical device. No, it's a lot easier to essentially build a Scrabble board of nuclear fuel and nuclear control rods for a more optimal heat distribution. For a realistically optimal heat distribution.
Remember that optical fibers need to stretch over many kilometers, so over that vast length, there's probably going to be some small impurities which make one polarization slightly slower than another. But unlike chromatic dispersion, which is measured in picoseconds per kilometer, PMD is measured in picoseconds per square root kilometer. Why is this? Let's construct a simple model and try and understand it. Let's send a pulse of light down the fiber made of only two polarizations, one vertical and one horizontal. Let's define the dispersion as the time taken for the vertical one to reach the end minus the time taken for the horizontal one to reach the end. So if the vertical one moves faster, then the delay between them is positive, and if the horizontal one moves faster, then the delay between them is negative. We're interested in the absolute value of the dispersion, but keeping track of the sign is also going to be important. Now, there's going to be random impurities in the fiber, tiny defects from the manufacturing process. Each impurity will randomly cause the vertical and horizontal polarizations to move either faster or slower, making the dispersion either increase or decrease. Let's be super rough and assume that the dispersion has a 50% chance of increasing by some fixed amount every meter, and a 50% chance of decreasing by the same fixed amount every meter. What we now have is something called a random walk. What we're interested in is how far this random walk moves away from zero, and the expected value of this quantity turns out to be proportional to the square root of the length of the random walk.
So this is reminding me of RMS, or root mean square, measurements of electrical signals. Use this a lot in nuclear power plants on our more critical, sensitive electronic signals. So things for things like sensors, transmitters, basically things that tell us what the reactor is doing. Which is grateful for AC current applications because they follow a sinusoidal wave pattern. So I can definitely see the similarities here. And it's really more of an effective value. And it usually figures out to, like, say, for voltage, for instance, is your peak voltage divided by the square root of 2. And those are the numbers that usually show up when, say, a technician takes a reading off of a multimeter. And that's the number that's usually used when you look at the magnitude of your signals. It's cool to see that, to see a couple of concepts I'm familiar with into a topic that I'm less familiar with. It just kind of shows how everything's connected.
I'm not going to delve into the details of why this is, because this video is already long enough as it is, but it's not too hard to prove. So what this means is that the total absolute dispersion, measured in units of time, is, on average, equal to some constant times the square root of the length of the fiber. In order for the units to cancel out, this constant, which is the PMD of the fiber, has to be in units of time divided by square root length. Which is why, if you look up a specification for an optical fiber online, under polarization mode dispersion, you will find a quantity measured in picoseconds per square root kilometer.
Nice.
I have seen other strange exponents on units. While doing research for this video, I found a paper on pulsar scintillation, whatever that is, which involves something called a scattering measure, measured in units of parsecs times meters to the minus 20 on 3.
Yeah, whatever that is. I mean, I know pulsars are massive rotating neutron stars, generate powerful signals, so I guess the people that look in that, but negative 20 over 3 is pretty funny.
I personally find picoseconds per square root kilometers more cursed though, just because square roots themselves are also kind of janky. Funnily enough, the optics assignment wasn't the only encounter I had with random walks in 2021. I was also doing a research task involving stretching polymers, specifically DNA, and from Monte Carlo simulations, I found that the sidewards deviation of a DNA molecule also followed a random walk depending on the length of the DNA, which makes sense because a polymer has the literal shape of a random walk.
Alright, I think he's lost me at this point. I don't know anything about DNA polymers.
What's weird about this random walk is that the length is measured in nanometers, while the sidewards deviation is also measured in nanometers. And so with a bit of hand-waving, I was able to include in my research paper the most cursed unit I have ever written, nanometers per square root nanometer.
That is awesome. I hope your paper got good reviews just for that reason. Or, I don't know, maybe if it was something that you just snuck in there, maybe nobody bothered to look at it. It's a little secret message Easter egg in there for people that are into this sort of thing. As far as my thoughts on cursed, what I actually think is the most cursed within nuclear engineering is probably the Röntgen, and that's because it shows up in popular culture, and yet it's such a weird unit, and that's because to me it's counterintuitive and not that useful by itself as far as calculating what radiation does to the human body, because that's what most people are concerned about, are the health effects of radiation when you talk about how radioactive is something. But what a Röntgen is 2.58 times 10 to the minus fourth coulombs, which again is a unit of electrical charge per kilogram of air. And this is dry air at standard temperature, pressure. So it's going to even be a little different based on the humidity. So it's not even that consistent. And the units we care about is rem or sievert, because that takes into account the radiation effects and what it's going to do to the human body. And that is simply just joules per kilogram multiplied by some constant based on what type of radiation is. It's 1-to-1 for stuff like gamma radiation, but can be anywhere from 5 to 20 if you get hit with neutrons, depending on the energy level of the neutron. A Röntgen is 0.877 rad in air. It's material dependent because, again, a Röntgen isn't really dose. It's more of exposure and ionizations. And the main reason why I think it's cursed is because I keep seeing it show up in various media as if it was rads or rem.
Have you encountered any other cursed units? Put them in the comments. I want to see the most ridiculous units known to science. I think all the places where science is mathematically beautiful are massively overrepresented, and sometimes it's just fun to see all of the places where the universe is completely gross and inexplicably awkward.
I love it. I really appreciate the request on this one. It's also interesting to just know how much overlap there is in various fields of science. Thank you very much for watching. I'll see you next time.